I want you to picture a pipe, but not the PVC pipe under your kitchen sink. I want you to visualize a steel artery, 30 inches in diameter.
Yeah, it is massive.
Right. It is wide enough for a small child to crawl through, though you absolutely wouldn't want them to.
No, definitely not.
Because inside this pipe, natural gas is just roaring. And the pressure, we aren't talking about a garden hose here. We are talking about 500 to 1,400 PSI.
Just to ground that number for everyone, your car tire is sitting at about 35 PSI. So we are talking about forces roughly 40 times greater than that.
Wow.
Yeah, it is roughly 100 kilograms of pressure pressing against every single square centimeter of metal.
That is a terrifying amount of potential energy. It's basically a bomb waiting for a spark.
It really is.
And in that environment, you can't just walk up to a control panel, flip a switch, and hope for the best. If you open a valve that should be closed or close one that needs to be open, you aren't just breaking a machine. You are looking at a catastrophic failure.
Right. And that is exactly why the machinery we are doing a deep dive into today, these massive gas compression sets used by solar turbines, they don't rely on a human operator standing there turning a giant iron wheel.
Like you see in those old submarine movies.
Exactly. No iron wheels here. They have a brain, a really rigid automated logic.
And that is what we're unpacking today. We have a stack of technical documents here regarding the operational logic of solar compressor yard valves. Now, I know, that title sounds incredibly dry.
It sounds like something you'd read to fall asleep, honestly.
It does, but when you actually read the source material, it's a thriller. It is a high-stakes choreography where millisecond decisions keep a facility from disappearing into a crater.
It is a choreography.
Yeah.
But before we get into the dance steps, let's set the stage for you. Where exactly are these machines living?
Usually in one of two places, both crucial to the global economy. They're either out on an oil production platform in the middle of the ocean, taking gas and re-injecting it back underground to force more oil up.
Or they're sitting on a pipeline, these lonely outposts pushing gas thousands of kilometers across a continent to heat homes and power cities.
And the setup is pretty standard, right? You've got a massive turbine, the engine driving 2 or 3 compressor bodies.
Correct. But here's the thing. The turbine is just the muscle. It's the brawn. The valves are the gatekeepers.
And our mission today is to decode exactly how those gatekeepers decide what to do, because the source material is very clear on one thing. Safety is first, last, and always.
Absolutely. So let's walk through this logic. Let's pretend we are standing in the control room. We're looking at a solar compressor set through the safety glass.
Okay, I'm picturing it.
It's currently off. It's in what the documents call a depressurized condition.
So what does that actually look like on the schematic?
Well, if the unit is off and depressurized, the valves are in a very specific lockdown configuration. The suction valve, where gas comes in, and the discharge valve, where gas goes out, are both closed hard. There's also a loading valve, which is also closed. The machine is effectively isolated from the terrifying pressures of the main pipeline.
But not everything is closed, right? Because if you seal a box perfectly, pressure can build up just with temperature changes.
Exactly. And that brings us to the most crucial safety detail of the off state. The surge control valve, and most importantly, the vent valve, are open.
Open to the atmosphere.
Right, open to the sky.
Yeah.
Because if the machine is off, you want any stray gas that leaks past the seals to have an easy path to escape, rather than building up inside the compressor case.
Okay, so we're locked down, suction closed, discharge closed, vent open. The machine is essentially asleep. I walk up to the panel, coffee in hand, and I want to start this beast up.
Naturally.
My instinct says, let's get compressing, turn the key. But the logic says, absolutely not.
Right. You cannot just start compressing immediately. And the reason is invisible. It's oxygen.
Wait, hold on. If the pipe is depressurized, surely it's just empty. Why do we need to worry about oxygen if there's nothing in there?
Empty is a very relative term in engineering. If a machine has been shut down and depressurized for maintenance, maybe a flange was opened, or maybe just the temperature changes caused the system to breathe.
Ah.
Yeah, air and the oxygen in it can sneak into the pipework.
And since the pipeline is full of hydrocarbons.
Exactly. If you have a pocket of air trapped in there and you mix it with high-pressure natural gas, and then you introduce a spark, or even just the heat of compression.
You've built a diesel engine the size of a building. Boom.
Precisely. So the very first step in the logic is the purge. Before the turbine even thinks about spinning up, the system has to flush the line.
Okay, so how does a dumb computer know the air is gone? Does it have a sensor? Like a nose that smells the oxygen?
You would think so, but no. Sensors can fail. Sensors can get dirty. The logic relies on something much more reliable. Math.
Go on.
The control logic sends a signal to open the loading valve. This lets a controlled amount of gas into the system. But, and this is the key, the vent valve is left open.
So you're pushing gas in one end and letting it blow right out the other, carrying any air with it.
Right, it's sweeping the room.
So to answer my question about how it knows, it uses a timer.
Yes, but it's not just a random 30 seconds and hope for the best. The engineers calculate the exact physical volume of that specific pipework. Every bend, every valve body.
They know the exact flow rate of the gas.
Exactly. And they calculate how long it takes to displace that volume, not just once, but usually 3 or 5 times over.
So it's a statistical safety net.
It is. The purge timer is set based on physics. If the pipe is huge, the vent stays open longer. If it's a small unit, it's shorter. Only once that timer hits 0 does the logic say, okay, statistically, it is impossible for oxygen to remain in this pipe.
And
only then does the vent valve slam shut. Now you have a system filled with pure gas, no oxygen.
Okay, so the air is gone, the vent is closed. But we still have a problem, right? The pressure inside our compressor is now just whatever the low pressure gas was that we used to purge. But outside, in that giant 30-inch pipeline, it's 1,000 PSI. We can't just open the front door.
No, you absolutely cannot. This brings us to the next phase, the equalization game, or technically pressurization.
And this introduces what I think is the most dramatic instrument in this whole setup, the differential pressure instrument.
It really is the killer metric. This instrument is the judge and jury of the startup sequence. It is constantly measuring the difference between the pressure inside your compressor and the pressure in the main suction header, the pipeline supply.
Why is that difference so important, though? Why can't we just open the valve and let the pressure equalize naturally? Think about a dam.
That's a great analogy.
You have a massive weight of water on one side and nothing on the other. If you just crack open the floodgate, the force of that water rushing through the gap is destructive. It rips metal apart.
Exactly. So if you're at 50 PSI inside and 1,000 PSI outside,
and you open that main suction valve,
that gas is going to rush in at near sonic speeds. It will hammer the compressor seals, it will destroy the bearings, and the shock wave could actually rupture the pipework. It is extremely dangerous for anyone standing nearby.
So the logic prevents that door from opening.
Strictly. The rule is absolute. The logic will not command the suction and discharge valves to open until that differential is low, meaning the pressures are almost exactly equal.
So the loading valve we opened earlier, that's still trickling gas in, slowly filling up the space, like filling a bathtub, until the pressure matches the pipeline.
Exactly. It's a gentle ramp up. And once that differential pressure instrument gives the thumbs up, once it sees the pressures are equal, then the magic happens.
The main valve's open.
Yep. The main suction and discharge valves swing open and the loading valve closes. You are now fully connected to the pipeline.
Now, I noticed a very specific warning in the source material right around this section. It talks about the control panel having a manual option, and the tone of the text changes completely. It stops being technical and gets almost aggressive.
It really does. It says never, never force or jumper yard valves.
Never, never. That's a double negative. You don't see that in technical manuals very often.
It's emphatic for a very good reason. The system allows for manual control because sometimes during maintenance when the machine is dead, you need to test a valve. But the source explicitly warns that this is only for competent personnel.
It feels like the machine is saying, I have calculated the safety margins. If you override me, you are on your own.
That's exactly what it is. If you try to force a valve open when the computer says no, if you think you know better than the differential pressure instrument, you are bypassing all those safety checks.
You are essentially hot wiring a bomb.
Right. If the switch positions don't match the logic, the sequence aborts instantly.
It just refuses to play.
It refuses to let you blow it out.
I love that. Okay, assuming we haven't touched the forbidden buttons and the pressures are equalized and the valves are in the right spots, only then does the system issue the command, ready to crank.
Which is funny terminology, Crank. It sounds like we're starting an old Model T Ford.
Yeah.
But we're actually lighting a massive industrial turbine.
So the turbine ignites. It starts spinning. But we aren't pumping gas yet, are we?
Not yet. The turbine accelerates to what they call IDLE speed. The source mentions the Mars unit specifically here, noting the power turbine breaks away at approximately 50% NGP.
NGP, what does that stand for?
Gas producer speed. It essentially means the engine has to be spinning pretty fast, half its maximum speed, just to get enough torque to break the inertia of the compressor. These are heavy, heavy pieces of metal.
So the turbine is screaming at idle, the compressor is turning. But wait, if the compressor is turning, it's moving gas. Where is that gas going if we aren't pushing it down the pipeline yet?
We are in a unique state called the idle loop or recycle mode. Remember the surge valve?
That was the one that was open at the start.
Right, and it is still fully open. So the compressor is sucking gas in, squeezing it, and then sending it right back to where it started. It's circulating in a loop.
Why though? Why not just push it out?
Because the turbine is only at idle. It's not spinning fast enough yet to build up more pressure than what's already in the pipeline.
It's like trying to merge onto a highway when you're only doing 10 miles an hour. You can't get in.
Perfect way to put it. You can't get in. So you recirculate until you have speed.
But isn't there a problem with just spinning the same gas around and around? It feels like running on a treadmill in a winter coat.
That is a great analogy. Huge problem. Physics dictates that when you compress gas, you create heat. Lots of it. If you take that hot gas, feed it right back into the front of the compressor, and squeeze it again, it gets hotter.
And hotter. It's thermal runaway.
Very quickly. The source notes that if the inlet temperature gets too high, the unit trips and shuts down to save itself. So if you want to stay in this recycle mode for any length of time, say to warm up the engine, you need large gas coolers.
You have to chill that gas instantly before sending it back around the loop.
Exactly.
Okay, so we're idling, we're looping, the gas is cool enough. Now, the operator says, let's go, put it on load. This is the transition to going live.
This is the moment of truth. The turbine accelerates from IDL to loading speed. And as it speeds up, the logic tells the surge valve, that bypass loop, to start closing.
So it's cutting off the escape route.
Exactly. Imagine putting your thumb over the end of a garden hose. As the valve closes, the pressure inside the compressor discharge shoots up.
It has nowhere else to go.
Correct. And there's a crossing point. The moment the discharge pressure inside the machine becomes just slightly greater than the pressure in the pipeline outside, the gas forces its way past the discharge check valve and flows out into the world.
You are now exporting gas.
Yes.
And the surge valve.
Fully closed, ideally. But this introduces the most complex and honestly the most violent concept in the documents, the surge line.
Yeah, I wanted to dig into this. We hear the word surge and it sounds like a wave, just a flow of water. But in a compressor, it's something much nastier, isn't it?
It is entirely destructive. To understand surge, you have to understand that the compressor blades are aerodynamic wings. They're pushing the gas forward, but the high pressure in the pipeline is constantly pushing back.
A stalemate.
Ideally, the compressor wins. But if the compressor slows down or the pipeline pressure spikes, the gas can snap back.
What do you mean snap back?
I mean, the flow reverses direction instantly. Imagine you are pushing a heavy boulder up a steep hill. That's the compressor working. Suddenly you slip. The boulder doesn't just stop, it rolls back over you.
Ouch.
In a compressor, the gas violently rushes backward while the blades are still spinning forward.
That sounds incredibly loud.
It sounds like a cannon going off. Engineers actually call it barking. It bangs and shudders. It's like a sledgehammer hitting the rotor shaft. A few seconds of heavy surge can destroy a machine worth millions of dollars.
So the logic is obsessed with this line.
Obsessed. It calculates exactly where that cliff edge is. As long as you stay clear of the surge line, the valve stays closed. But if the logic sees you getting too close, maybe the pipeline pressure spiked unexpectedly, it will automatically crack that surge valve open just enough to relieve the pressure.
It feathers the throttle to keep the machine from stalling.
It protects the hardware from itself. Always.
So we're running, we're pumping gas, everyone is making money, but eventually we have to stop. And the source describes two very different ways to stop. There's the normal stop, which is polite, and then there's the fast stop, which is less polite.
Putting it mildly.
Let's start with the normal stop.
This is a highly controlled scenario. Maybe operations needs to do some maintenance on a different part of the plant, or they just don't need the gas for a few hours. But, and this is key, they want to keep the machine pressurized.
Why? Why not just drain it and turn it off completely?
Because venting 30 inches of pipe takes a lot of time. It creates a massive amount of noise, and it wastes valuable gas. If you're only stopping for 2 hours, you don't want to have to do that whole purge and pressurized dance we talked about at the beginning.
You want to park the car with the engine off but the radio on.
Exactly. So how does the logic handle that? First, it slows the turbine down to IDLE. The surge valve opens, so we go back to that recycle loop.
Right.
Then the normal stop command is issued. The suction and discharge valves close tightly. The machine is now isolated from the pipeline again, trapping the high-pressure gas inside it.
It's a pressure vessel now.
Yes. And then the turbine cools down and shuts off.
Yeah.
But this state, the hold, is incredibly delicate.
Why? It's just sitting there.
It's a nervous wait. The system is desperately trying not to open the vent valve. But there is a strict checklist of conditions that must be met to keep that vent closed.
Like,
Well, the biggest one is lube oil. Even though the turbine is stopped, the bearings are still hot. So there are auxiliary pumps, post-lube pumps, that keep oil flowing. If the logic detects any issue with that oil pressure or temperature, it triggers a fast stop alarm and boom, the vent opens.
it dumps the gas.
Immediately. Because if the bearings fail, the gas seal might fail. And if the seal fails, gas leaks into the room. So better to vent it up the stack.
What else?
Fire alarms, obviously. If the fire system even twitches, the vent opens instantly. And finally, there's usually a timer, a pressurized hold timer.
So you can't leave it pressurized forever.
No. If the timer runs out, say, after 4 hours, the logic says, okay, we've waited long enough, this is no longer a short break, and it opens the vent to depressurize the unit.
It's amazing how many if-then statements are governing this thing while it's ostensibly doing nothing.
It's never really doing nothing, it's always watching.
Okay, that was the polite goodbye. Now let's talk about when things go wrong. The fast stop.
This is the emergency logic. We are talking high vibration, a fire detected, or a sudden loss of oil pressure while the unit is running at full load.
The source says the unit needs to be shut down immediately.
Immediately. And the pacing here changes completely. This isn't a negotiation, it's a reflex.
Walk us through the split-second timeline.
The fuel valve slams shut. Power is cut to the fuel shutoff. But the real drama is in the yard valves. Everything happens simultaneously to save the machine from tearing itself apart.
What's the biggest danger?
Surge. Remember, if you cut the fuel, the turbine loses power instantly. It starts decelerating fast.
Right.
But there's still high pressure in the pipe pushing back. That operating point is rushing toward the dangerous surge line.
It's about to stall and break the shaft.
Right. So the logic doesn't just tell the surge valve to open. It actually cuts power to the valve's air solenoid.
What does that do?
It vents the air, holding the valve closed. It causes the surge valve to pop open as quickly as physics allows. It's a failsafe. Even if the computer crashed, the loss of power opens the valve.
So it dumps the pressure into the recycle loop to save the machine.
Exactly. Moving the operating point away from the cliff edge, at the exact same moment, the suction and discharge valves are commanded to close.
Okay, isolate the problem. That makes perfect sense.
But here is a nuance that I found fascinating. The vent valve, the one that releases gas to the atmosphere, is commanded to open, but not yet.
Wait, if it's an emergency, if there's a fire, why not vent immediately?
Because you have to confirm the suction valve is closed first.
Oh, of course.
Think about the logic. If you open the vent valve while the suction valve is still sticking open, you aren't just venting the compressor. You are venting the entire 1,000-kilometer pipeline.
You drain the whole system. That's millions of dollars of gas.
In a massive environmental event. So the logic checks, is suction closed? If yes, then open vent. It's a failsafe within a failsafe.
And after the dust settles.
The unit takes minutes to discharge that trapped gas. The oil pumps run their post-lube cycle to save the bearings as the turbine coasts down. And hopefully you have a machine that is intact and ready to be fixed.
It's incredible. You know, we drive past these facilities or see pipelines on maps, and we just think of them as static infrastructure, just dumb pipes. But hearing this, it's like there is a constant, high-speed mental calculation happening every second.
That's the real takeaway for me. The startup is this careful, slow dance of equalizing pressure, managing heat, checking the math. You can't rush it. But the shutdown. The shutdown is a martial art. It's a split-second reaction designed to protect the hardware from itself and the facility from the gas.
And it prioritizes that safety over production every single time.
Every time. If a sensor drifts, if a valve lags, the logic doesn't guess. It aborts, it vents, it shuts down.
Which brings us to a final thought for everyone listening. We place so much trust in this logic. It's invisible code governing explosive forces. But logic is only as good as the data it receives.
That is the critical question. The logic relies on that differential pressure instrument or the temperature sensor in the bearing. What happens if the sensor doesn't fail completely, but just drifts? What happens if it tells the logic that the pressure is equal when it's actually 100 psi off?
The logic would blindly follow the bad data. It would open the valve, and the result would be exactly what the logic was designed to prevent. It makes you realize that in the world of heavy machinery, the most critical component might not be the steel turbine blades, but the tiny sensor telling the brain what's happening.
A sobering thought.
Indeed. Something to chew on the next time you turn on your gas stove and that blue flame just appears. That's it for this deep dive into the logic of pressure. Thanks for listening.
Stay safe out there.